Sui. Today I want to have a look at this article. This programming language that I stumbled across, and it comes with an article. The link on the GitHub page, which I thought was interesting. I started reading it, and I was like, okay, this is actually kind of interesting, and I kind of just want to go through it in more detail. So, first of all, what is this Moo thing? I mean, I'll link it in the description if you want to have a look in more detail. But it's like assembly abstracted, I guess. I mean, probably the best way to actually describe it is just look at the actual code. Um, so, for example, I don't know, array.mu, I guess. Like, you can see that you have. Okay, actually, it's kind of hard to see, I'll be honest. But like, you have like a function here, right? Function definition, go slide up. I don't fully understand all the syntax, but like, you got your arguments here. The return type, I'm guessing, is maybe somewhere. You do have like if control statements, so you have like some control flow stuff. This looks like a scope, a local scope. So like honestly, like I mean, the joke is that if you try making if you try abstracting assembly like any level, you're pretty much just going to end up with like a worse C, or a better C. You know, maybe a Zig if you're particularly skillful with it. But like you can see, this is quite conservative with the features it gives you. Like here you got a var a, and then I guess in the slashes like specifies you want to put this on the what's this, the ESI, which I think is the instruction pointer, or like the stack. I can't remember my registers. Goddamn. But you got ECX and EDX as well. Those are registers. You can see you got like the arrow for assignment, which I guess is like a move, and then like copy would be like, well, copying it. So it's interesting. It's interesting. But anyway, the language is one thing. The main thing I want to focus on is this paper, because it's quite interesting indeed. So, bicycles for the mind have to be see-through. What the hell does that mean? I don't know, but let's get into it. This paper describes ongoing research on building software to be comprehensible to its users so they can tailor it to their needs in the field. Um, Sorry, I haven't really introduced what I'm actually doing. I'm just gonna read through, I'm gonna read through this research paper and kind of just give my thoughts in it. Because I've been thinking a lot of myself about programming language design. Is something I'm very passionate about, and this one particularly stood out to me because one thing I really wanted to think, because like, okay, I'll say there are kind of just two. I mean, you don't have to obviously subscribe to. Well, there are two like camps of thought, like extremes, and one is I want no hidden control flow. No hidden control flow. It's what C programmers swear by. It's what Zig tries to swear by as well. They want to give you everything up front. And the other camp is abstraction. Just specifically zero cost abstraction. I guess there's a third camp, which is you know, we don't care about performance. We just want our code to look nice, and that's like the Haskell crowd. But I mean, like for systems programming, which is like of like actual like efficient programming, like performance efficiency, you have we want to see everything that's going on, and we don't care about what's going on as long as it gives us a clear mental model for again, zero cost abstractions. And yeah, I mean, I said like you have these two camps, but I'm really torn between them, right? Because like I definitely see the value of no hidden control flow, but at the same time, it's so tedious. Like it really is tedious, and it's really hard to scale. Like you're gonna need abstraction at some level. Like you could say a function is like, it's like, yeah, like functions is a good example, right? Functions are useful because they let you. I mean, like on a system on a hardware, like at the low level, a function lets you store the same block of code and then call it at runtime. So you're not like just repeating the same thing, which is useful if you have like caching, or if the function is particularly big. If it's a small function and you inline it, but like then okay, if functions can be inlined, why do we have functions at all then? Like why do we bother with functions that can be inlined? Because that means, I mean, inlining, if you don't know, just means the function stuff at compile time gets copy pasted into the code. So like it's not actually being called at runtime. And well, that's because function creation is also a form of abstraction, and it's hiding the control flow. I mean, it's not hiding the control flow, but like it's hiding like the implementation details, um, which I think is cool. But at the same time, there's merit to hiding stuff. Not hiding, but like just like abstracting it away, so you don't really have to worry about it. Like RAII which I think is pretty cool. Which like with classes having like automatic destructors and scopes. I think that's pretty cool. And I think there's definitely like again I said two camps. I think there's some intersection between them, like a sweet spot that we can reach. But for now, it seems like with we're in a very exciting time of languages where we have like Rust, which is really pushing these zero cost abstractions, and Zig, which definitely borrows stuff from Rust and like ideas from functional programming, but at the same time wants to be more like C with explicit allocators even that you have to pass through. I mean, I haven't used much Zig to be honest. I've used more Rust, and I want to get into Zig later, but I have used C and C++, and yeah, there's a lot there. So the fact that you have assembly and someone wants to just kind of take assembly and make it more easy to like make it easier to reason about with like variable names and all that kind of stuff. And as we saw in the thing, we have like functions, right? But at the same time, keep the control flow like not only control flow, keep like the process, like what's actually going on at the low level. Keep that so clear. So like you're never worrying like, oh, well, will my compiler optimize this correctly for me? Like no, like you're at it by hand. I mean, at least I assume that's what this largely does. Maybe there's some optimizations that happen under the hood, but for the most part, I assume it's fairly in the control of the programmer. So let's have a read of this. And see what we think. So, this paper describes ongoing research on building software to be comprehensible to its users. Very important. So they can tailor it to their needs in the field. And already this is interesting because one thing I was wondering about is you can have DSLs, right? Domain specific languages. And like people will think, okay, like CSS is one, HTML, but you can also have DSLs that are still like proper programming languages, right? Like you can advertise C++ or Rust as a general purpose language. You can do anything in it. You can do web dev in it. You can do systems programming in it. You can do whatever you want, game development. But ultimately, they kind of fall short in some areas just because it's really really difficult to create a language that is truly not just well equipped for any field, but best equipped for any field. Like the ultimate super language that can be used for anything and will be better than any other competitor in that field. That is really difficult. And I do have faith in Rust or some Rust inspired future language that can maybe one day pull something like this off. But for now, I just don't feel like it's gonna happen for a while. Or like at least like people aren't approaching it the right way. So like with this, tailor it to their needs. I mean, okay, well, this is talking about building software, but like I know obviously it's talking about a programming language as well. I think there needs to be well, I think what will probably happen is that before we create this perfect language that occupies all fields, we need to first create perfect languages in specific fields. Like we need the perfect systems programming language, the perfect web dev language, and then eventually we can see how we can combine them. Anyway, our testbed is a computing stack called Mu that I assume this is Mu like the Greek letter, me, but we'll see, that de-emphasizes a clean interface, really, in favor of a few global implementation properties. Small implementation size, oh, shout out Zig, few distinct notations, okay, so less to memorize, parsimonious dependencies, I don't know what that means, let's look that up. Parsimonious means very unwilling to spend money or use resources. Okay, so like conservative dependence. So being conservative with dependencies, I also agree. A simple dependency graph that avoids cycles, kind of similar, I guess, and early warning on breaking changes. Okay, I mean, what is a computing stack? Because like from what I can tell, this is just a programming language. Like I know what a stack is as a data type, but like what's a computing stack? I might need to actually clarify this. Like so far, I've just assumed it means language. Everything above the processor. Okay. Well, I mean, I guess that's where we start here. A human-scale computer, not designed to operate in large clusters, providing services for millions of people. It's designed for you to run one computer, running the code you want to run, and nothing else. Which is a bit confusing. Hopefully that becomes a bit more clear as you read on. But clearly, like it's very much a hobbyist language, and I think it even says, yeah, minimal dependency hobbyist computing stack. Because I'm guessing like the goal of this isn't to, you know, isn't to develop some Rust thing that can do anything. But I do wonder what the real goal of this is then. Because Moo again, like it seems like quite small scale. So when it talks about like having these things, I wonder if it's saying these because this is how you keep a language specific to a user, or if it genuinely thinks that this could scale to bigger languages too. Or at least if it doesn't talk about it, I sure will. Yeah, so there's a lot to break down here, but I'm sure I'll get into it later. So let's just move on. Assuming a 32-bit x86 processor, I'm 64-bit, and for now a basic third-party Unix-like kernel. For now, Moo builds up from raw machine code to a memory-safe but less expressive language in C. Interesting. Now, being less expressive than C is quite not an accomplishment, but it's certainly it's very low, right? Very low expression then. Um, but memory safe is interesting, and I do wonder how I'll do that because memory safety is obviously all the rage nowadays. Our approach to keeping software comprehensible is to reduce information hiding and abstraction. Once again, no hidden control flow, and instead encourage curiosity about internals. I'm very curious to see what that means. But also reduce abstraction. If you're watching this, let me know in the comments what you think about abstraction. I mean, it's a very vague term anyway, but like, I feel like more abstraction isn't bad as long again as it's zero cost. Our hypothesis is, but then like here, encourage curiosity. There is something to say about if it's so abstract that the programmer doesn't know what's going on. It's also problematic. Like people struggle with Rust, for example, because they just don't understand what the hell Rust is even doing. Like I feel like if you come from like C++ and you actually understand what Zig is doing behind the scenes, you can really use it effectively. But if you're like a new programmer and you learn Rust for the first time, you're going to struggle. You're going to struggle because you just don't understand what the abstractions mean, which is very interesting. Or I mean, you could read the book, but like still, our hypothesis is that abstractions help insiders who understand a project, but hinder newcomers who understand only that project's domain. Okay, that's if they're project-specific abstractions, but okay. Where recent efforts to create bicycles for the mind have tended to focus on reducing learning time and effort, we explore organizing the curriculum to be incrementally useful, providing an hour of actionable value for an hour or three of study. Jumping from 1 to 3 is interesting. I do wonder what bicycles for the mind, like, it's put in quotation marks. I assume this is like a thing. Oh, Steve Jobs. Tools that amplify human mental capabilities. Ah. Oh, okay. So it's like if you're walking, you're slow, but if you have a bicycle, you can go faster. But you're still using like your legs as opposed to like an engine. So like it's still manual, but you're okay. Um, yeah, okay, sure. Yeah, a, an hour of actionable value for an hour of study. Like, how are you measuring that? The hope is that rewarding curiosity, we'll see what that means, because I'm curious what it means by curiosity in this case, will stimulate curiosity in a virtuous cycle, so that more people are motivated to study and reflect on the difference between good versus bad design and good versus bad architecture, even as the study takes place over a lifetime of specialization in other domains. I don't know what that's talking about. I actually don't know what that means. Spreading expertise in design is essential to the creation of a better society, yeah, big scope here, of more empowered citizens. Okay, I'm trying to understand what this is saying. So, like, if someone is curious about something, they're rewarded for their curiosity. Like I get the idea, and like obviously it's a good way to learn. Um, like if I'm learning maths and like I'm curious about something, and then that curiosity leads me to a new discovery, that's like, oh, that's so cool. Like that's great to learn. So is it suggesting that, well, is it claiming that it can create a language like this, a programming language, where the more you learn about it, because like at some point you got to kind of reach a cap, like where you've mastered the language. Um, and then what? Like you just quit the language because you've got bored of it? I don't know. Software tools have a role to play in this process. They do, both by exemplifying good design, yeah, and by providing a visceral illustrations. Sorry, not a visceral, providing visceral illustrations of the consequences of design choices. Okay, that's funny. I love software development because design is so important. Like, if you have bad designs, the suffering it causes is just insane. I think humanity has really reached such an interesting thing with software development, because it really is the accumulation of like all our creative, organizational, scientific efforts to just make a tool for which we can create other things with easily. It's so interesting. Linguistics, psychology, like it's all there, honestly. CCS concepts. Okay, human centered computing. You say human centered, but you also say that abstraction we should what's the word? Reduce abstractions, which is interesting. Open source software. Okay. Software and engineering, life systems. Okay. Keywords. Blah 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 blah. Okay. Introduction. We're gonna quote: in order for code to be living structure, even the tools used to make the code need to be living structure. Okay. In tools for conviviality, even Illich, I guess, describes two schools of tool making. Okay. The means by which humans influence their environment. Oh no. Okay, so the tool schools are the means by which humans influence their environment. Okay. Manipulative tools focus on immediate productivity. They use what's easily available and convenient to use and build on it. Little attention is given to the process by which tools are created, leading to a deep dependency chains. Leading. Why am I adding particles to deep dependency chains of tools that needs other tools to be built? I'm gonna zoom in here because I don't know how small my screen is. Like for the quality on the thing. Over time, special interests capture the apparatus of toolmaking and management. Flaws in specific tools are papered over with more tools. What used to be considered the means towards some other end gradually turns into ends in themselves. Their production and nurturing requiring increases. Their production and nurturing requiring increasing quantities of manpower. What? What used to be What used to be considered the means towards some other end gradually turn into ends in themselves. Their production and nurturing requiring their production and nurturing requiring increasing quantities of manpower. I cannot read today, from people not motivated to work on this endeavor and therefore needing increasing amounts of management. Yeah, because like we have this idea that like, oh, if you're really good at programming, you can use assembly to like code Red Dead Redemption 2. But like it's just not feasible. Like humans are not like it's just not feasible. Like it's one thing to make like what is it, roller coaster tycoon in machine code, but to make there is a limit to just what humans can accomplish, and that's why we need better tools. And again, I mean, I'll probably say this a lot of times. Um, Humans in general, what's so special about humans, right? We have tools. We use tools. Okay, I mean, like not well. It's one definition because obviously other animals can use tools, but like we can really use tools, and we can use tools to make other tools, and then those tools make other tools, and then those tools make other tools. Right? Software, programming languages, and software in general are tools. Like it's like so. Having good tools is so important, and then again, like we need to have tools that are good to then also make good tools from them as well. Because if the tools suck, if the software sucks, it's a pain to use. You get stuck, and then you can't even complete the goal you wanted to go to because the tool just wasn't good enough. Like for your mind to kind of wrap around. So very interesting topic. In response, Illich proposes an alternative school he calls convivial tools. So we had manipulative tools and convivial tools. According to him, sorry. Okay, he is Austrian. Um, can I get like a how to pronounce?
Ivan Illich.
Ivan Illich.
Ivan Illich.
Ivan Illich, okay. In response, Illich proposes an alternative school he calls convivial tools. According to him, the primary goal when making a tool shouldn't be to just make some tactical activity more convenient. Instead, it should be to preserve the degrees of freedom of individuals as we explore alternative combinations of human and machine. Individuals should decide for themselves the uses to put their own manpower to. We should celebrate tools that preserve individual agency and shun tools that reduce human agency. So, okay. I mean, obviously AI is reduces human agency, but then also with like a language again like C or even assembly, you are responsible for so much. Okay. Concretely, if a tool doesn't do quite what you need, don't try to paper over its deficiencies with a second tool. The maintenance burden of both will lead to compounding claims on your time and on the time of others, thereby reducing the degrees of freedom of human society as a whole. Again, I love how this goes out to human society, but like we see it in like web dev, right? You have like these libraries that just depend on other libraries. In fact, Python. I tried to install like this image processing Python thing. It took like half an hour just because of like how many dependencies I had to install. Like honestly, quite incredible. Honestly, quite incredible. Um, and a very interesting topic because where do you draw the line and what you implement yourself versus what dependencies you use? And maybe there's something to be said about generic generic tooling because just because something is generic doesn't mean it is the best solution for every problem because there might be some specific implementation or like some specific case where focusing on just building something like a tool for that one case is better than a tool that works for that case but can also work for other things. Um, and assembly machine code generally doesn't isn't so generic friendly. C doesn't have generics without pre-processing, um, because neither does machine code. So very very interesting, very relevant, very relevant. Instead, take the first tool out and think about the problem anew. Okay, so I have this generic tool. I have this problem. My tool doesn't quite fit. Instead of papering over it, I'm going to create a new tool, I guess. Taking tools out of existing workflows is difficult. Our social arrangements incline us to take artifacts for granted once they've been introduced and experience some level of adoption. Very true. Very true, actually. I mean, lots of back and forth here, but like, just think about like even programming languages themselves. How hard is it to make C++2? It sounds so simple. Just look at the language, go through its flaws, and make a new addition, right? But it's actually so difficult because if you made a C++2, it just wouldn't be adopted. I mean, like even then, there are people who would use it, but just the amount of software that is dependent on C++ in its current state is just so huge that the C++ committee, the ISO committee, have and continue to decide that it is more worth their time to just update C++ instead. The existing one, um, because yeah, like this adoption, or like the web, CSS, HTML, JavaScript, like they're here to stay because we just locked ourselves in these dependencies. It's really frustrating. It's honestly really frustrating, and it's if this problem can be solved, it'd be huge, right? Like Rust has additions, which is really interesting, really cool, and Zig has well, Zig's goal is that it will only release when it's perfect or like good enough that it doesn't need more changes. I don't know how many years that's going to take, but anyway, people acculturated in our society tend to expect a level of specialization, with problems partitioned according to fairly static boundaries. Okay, but if they're not static, most people's careers are circumscribed by these boundaries. If we grow used to something that we don't know how to build or manage, the prospect of losing it is painful. I see. So, like, um, you have a tool that you depend on. If you lose that tool, you're kind of screwed, and then you have to like spend time learning a new tool. Yeah, like I mean, like right now, if you use let's say Visual Studio Code, right, or like JetBrains, like how hard would it be for you now to just give that up and then go ahead and learn NeoVim? Um, I would say, and I've watched like the Primogen, his take on this as well. He would say that just learn NeoVim, or like learn a new programming language. Not necessarily because like it'll be super useful to you specifically, but because it will just get you out of your comfort zone and get you trying different tools and like stepping away from those dependencies. Because like attaching yourself to a tool is such a crutch in software and outside of software. Like it's really quite, it's not talked about enough, honestly, and it's not acknowledged enough. If we stipulate that Illich's goal is desirable, sure, the problem then becomes how to encourage a greater dissemination of knowledge about tools. Yeah, dissemination meaning spread. Yeah, how do we build tools that can be maintained by end users in the field without support from authors and experts? I would argue we maintain by end users in the field. Okay, interesting. The Mu project explores one approach to this problem in the domain of software to support modification in the field, keep everything simple enough to be comprehensible by anyone without exception. Full stop. Mu is a computing stack designed from the ground up to have a strict complexity budget to fit in a single brain, to not grow complex over time, and to reward curiosity and encourage people to understand its internals. Very, very interesting. And this is why I wanted to make a video about this, because it does resonate a lot with me, but the execution of it is just so damn difficult to get right. And I don't think this project particularly gets there. Um, is there like an actual example that I can, like? I think there was like a Fizzbuzz would be nice or something. What's sub X? What is sub X? Is this like an older version of the language? Hmm, maybe. Like let's look at math circle. Look at math. So absolute value, compare n and 0, break if, negate, return n. Like, it's okay. But I just feel like break if arrow equals negate n. Like I feel like you can't, we have this idea of this. Hmm. I mean, two things here. The first one is to fit in a single brain. This is really difficult because if you if you don't abstract away stuff like registers, or in some cases even like type information, like specific types, like oh, U32 has a limit of, um, I mean I don't even know, like 4 billion, 4 million, 4 gigs, I think. Like that is mental overhead, and that is why abstraction can be useful because it removes that overhead, and you don't have to worry about it. So you just focus on the task itself. So this is a bit counter to what I see here, which is specific registers instead of just relying on like automatic conventions, like EAX as a return type. Isn't it always a return type? Like just generally speaking, um, like even if you had like a default that you could change, like it's still like at the back of your mind and it takes up space, which is very, again, like just really interesting. Touches on like psychology, and then to not grow complex over time. and reward curiosity. No, there's something else. Yeah, comprehensible by anyone. Which means like what? Like who's anyone? Like, can my 80-year-old grandma look at this and be like, "Oh yeah, I see what's going on." Like, even just to understand this, you need to understand a lot about computer architecture, which isn't simple, by the way. Like already we have an issue where the very tool that we are designing tools for itself is not simple. And that's not going to change, quite frankly. It's just not going to change. Like it's not so complicated, but there's just a lot to know. That to say that like to kind of aim for this comprehensible by anyone without exception, like what does that mean? Like that doesn't sound feasible. Because like compare, loop, return, and like if we have EAX and compare, like why not just do CMP? It's like, oh, because it's harder to read. Like sure, but then like it expands to compare. But then like EAX, like does that expand to something? You know, like this, like you could say 32-bit the 32-bit A register, or the lower 32 bits of the A register, or like for int, like integer, right? And like what is an int? Like what size is an int even? This uses int instead of like U32. I don't know. I mean, well, I have a strong yeah. I'm not seeing that reflected in the project. These goals stem from three major influences. In chasing large-scale comprehension without access to original authors, we try to follow the dictums of Peter Nahr and add detail to them. In emphasizing degrees of freedom, we follow Christopher Alexander. In de-emphasizing black boxes, we follow the observations of Gregor Kixalis and and the dialectic between his blah, 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 blah. Okay. Yeah. De-emphasizing black boxes. Obviously very counter to the functional programming ideal of just I have a black box. I give it an input, and it gives me a predictable output. But like, why is that bad? Like, I feel like black boxes are a really useful model of tooling because the whole idea is that it's predictable, it's consistent. You know, like it's well, to give an example, right now I'm on Streamlabs because OBS was just absolutely not working for me well. Like I couldn't get my camera to work. And I had no idea. Like I tried to like use Claude to kind of figure out what the hell's going on, but it couldn't figure it out either. And I'm just going in circles. Like that's not a very clear abstraction or like tool, whatever. Because like all of a sudden my thing just stops working, and I don't know why. Whereas if you have this like if like this ideal black box is one such that if I don't do anything different, then I will expect the same output, which is good because like you can reason about it, even if it's something that's like really complicated inside the black box. As long as I can see the inputs and outputs and like kind of understand what kind of like describe the transformation taking place, then I can reason about it. I can use that and then build on top of it, without without the mental overhead of what's going on inside. So I really wonder where this is going. This paper reports on progress towards his goals. Our hypothesis is that using fewer abstractions, carefully designed to leak in just the right ways, can make the maintenance task more approachable to end users. Since dependencies introduce their own abstractions, we minimize external dependencies. I don't know how dependencies would introduce abstractions any more than your own abstractions. I mean, I get the idea is like, I mean, here, in its thing, not there, but like in the README, it said this is for you, right? So like you make your own dependencies, and then you understand it. And that's cool, but it's not practical. It's good for learning how to program and learning how computers work, obviously. But you can do that in any language, right? Pretty much, or like open like C++ and then just learn that. by not using any like third party point. Like you could do that, or even just assembly, right? And then like build your way up from assembly. So like go from assembly to C, and then from C to C++, and from that to like you could do that. And then eventually you'd have built up enough knowledge to be really good in Rust or really good in Zig, right? So is the goal here an actual usable tool, or is it a programming language that teaches you how to learn programming? Because if it's the latter, then assembly exists, and I'm not sure how this is making that any easier. Like if anything, it just looks like it looks like a weirder C with I guess more low level control and less dependency on compilers. And yeah, because compilers as well. Yeah, okay. In particular, since most mainstream software prioritizes use as a black box rather than comprehension of internals, for good reason, we try to minimize dependencies on mainstream software. Yeah, I mean, this is just the introduction, but like, what's his reasoning for why a black box is bad? Or like, has he considered the benefits of a black box approach, which again is that we don't want to have to think about the internals? Like, with a black box, you can either understand the internals or you cannot, and the result is the same. Maybe just that if you understand the internals, then you can use it better. Um, so like really the only bad thing is just, or like the only thing to really like the what do you call it? The mitigating factor, I guess, is just do you understand the internals? And then that can be done by how clear the internals are documented, right? In the case of code, then if it's good self-documenting code, then it's fine. But like removing the black box is just like, then what is your code? Like if I create a function called abs, like how is this not a black box? Like it is. I'm just opening it up to read the implementation details, which I can do with the black box anyway. I mean, again, I guess the idea is that a black box is hidden from you, but like any good open source software would just let you see it. So I don't know. We don't have to have. In fact, I'll say more about this. In Haskell, for instance, when I wanted to learn more about monads and all this kind of stuff, it was really useful for me to just look at the source code of how they're defined, or like I mean, yeah, I mean, like that was like my first proper experience of looking at source code because before that I would use C++ and reading the C++ implementation for like compilers. It's a nightmare. It is a nightmare, and it takes a special level of expertise in of itself. Um, but again, that's not a black box problem. That's a unreadable software problem. We don't have a definitive conclusion yet on the efficacy of this approach. If we fail to falsify our hypothesis, we'd like for Mu to demonstrate an alternative way for people to collaborate over software. Collaborate, okay, by exchanging complete working stacks. All software running on a computer, with the possible exception of firmware, as opposed to like the cloud, designed to be manually merged for individual contexts, like Git, I guess. We hope taking control of it. Like, what? What? Well, why does it matter if it's like cloud based? We hope that taking control of the developer experience in this manner will lead to more comprehensible software infrastructure. Comprehensible. Okay. So it seems like comprehension is the kind of the key focus here. And like I see the efforts, but again, like throwing it's kind of also focusing on the wrong things. Or like maybe misunderstanding what like some of these things are, like abstraction of black boxes. All right, let's see. I'm turn my lights on real quick because it is getting darker. So, strategies. Move aims to accomplish its goals using the following strategies. It almost unfailingly implements high-level constructs out of lower-level ones. Dependencies flow down, and we avoid cycles in the dependency graph as far as possible. Yeah. So, what kind of drew me again to this idea, or like to this language, is I very much like this Lego, this building blocks approach of well, a programming language where you can start at like the lowest level and in the same language build up higher and higher abstractions. But keyword on abstraction. Like here says high level construct. That means abstraction, right? So what's the issue with abstractions then? And then here says avoid cycles in the dependency graph. But like, how would you have cycles anyway? If you have circular dependencies, then your code just won't compile. Um, Unless I'm mistaken, but like I've had issues with in C++ with like library design where I kind of have to end up having circular dependencies just because of how bad the include system is as a module system, right? Which is one major reason I switched to Rust just for the modules. But like yeah, like I couldn't have dependency cycles anyway, so I'm not entirely sure what it means by that either. But yeah, I mean, like this, I'd really, I'd love to see a language that lets you just build up, like literally you start at assembly, and then that goes up the chain to higher abstractions. Like imagine if you could look at like something that reads like Rust, and then as you go into its functions, and like go down the chain of dependency. Oh, I mean, not dependencies, but like go down the implementation chain. In Rust, you would eventually get to not like assembly specifically, but like an assembly like code where you are literally doing machine instructions line by line. That would be so cool. Um, and then you wouldn't even need to implement a compiler because it would just using like these conditional like okay, like if it's this, then jump to this, then like you'd actually have a self-compiling program. Like you just execute it and it expands the functions and then through its control flow and then like it just follows that and then you have your bytecode. That's cool. I do wonder that would be a very cool language. I actually I don't even know if that would like it sounds like something that would compile slowly. Um, because compilers do more than just expand code. Like they can also cache stuff and whatnot. But I just wonder like yeah like there's gotta be a way. That's a language I'd really like to see, and it's what I kind of wish this one was. Um, but so far I'm not seeing it. Anyway, I'm gonna stop throwing shade at this language. I'm really here for the paper. So it uses as little mainstream code as possible. Okay, so like for printf, don't depend on C, libc. It uses as few notations as possible. So like less things to remember, which fair enough. But like, sorry, I just said I'm not gonna throw shade at this code. I'm gonna use that like for reference. Um, yeah, few notations. Did you know that there are like yeah, how many assembly instructions are there? I mean, obviously it depends on different languages, but different implementations. No one outside Intel really knows. Okay. Point in case, there are a lot, right? Way more than you could remember. But like you don't really use that many anyway. Like ultimately you use some for really niche cases, but for the vast majority of them, you'd probably like with cases, you'd probably only use like I don't know. I mean, I'm not gonna pretend like I've written like a full game in assembly, but I would assume you don't need more than like 50, more than 100 maybe, um, to get by. So, and then like even then, for other languages, like for Rust, for instance, there's not that much you need to remember. I actually think Rust is quite easy because like it's pretty straightforward. The hardest thing is just the macros, like understanding the macro system and how to write that because like that's like a whole other language in of itself. But even then, like I don't see how this is better. It uses as few notations. Okay, it prioritizes safety over syntactic convenience. I would argue that you can have both at the same time. So, but yeah, obviously, if you can have safety in a case where you can't have syntactic convenience, then fair enough. It focuses on encoding intention. Huge. The ideal, if making a change raises no errors, then no regressions should have occurred. Regressions like what? Uh, like you don't have to obfuscate your intention. If an error is raised, it should be obvious to an end user that the expected behavior is superior to the erroneous behavior. So, like, if an error occurs, it's on purpose, I guess. But yeah, intention is a huge one. Commons, obviously, I mean, commons can do that, obviously, but really, it goes down to self-documenting code, doesn't it? And then Kojo chooses to fork it, both technically and socially. Okay, I guess that's kind of just something you can't really control. It's more like a product of how easy your code is to read and how useful it is to others. But here's how these strategies support Moo's goals. So minimizing dependencies reduces the number of moving parts and therefore the total cognitive load of the stack. Is the stack the computer stack or your memory? Like your brain. Keeping dependencies decomplected. Okay. Also aids comprehension. I mean, I know there's a reference, but I don't want to jump down. Like decomplicated? Like complexity? I don't know. When learning a strange new code base by oneself, meta-circular implementations are hard to understand. They can seem like circular reasoning. I really want to see an example of what this meta-circular implementation is. Like, if it seems like circular reasoning, is it not circular reasoning? Because like, it's code. Like, code needs to function. Like, it would be erroneous, would it not be? But okay. Mainstream software isn't as disciplined about avoiding or topologically sorting dependencies. Using it violates the previous rationale. Mainstream. And that's a very broad net, but okay. Mainstream software is usually designed to hide implementation details behind an interface, which goes against our plan to expose implementation details but keep them simple. Okay. Actually, I'm gonna look for another example here, because like, at what point does it not become simple? Are these comments? Ooh, okay. It's a type. Hmm. Okay. Um. There's a lot here. Any mainstream software we introduce is a source of noise when we try to falsify our hypothesis. We'd like to be confident in a negative result rather than wonder if, say, the C compiler we use hindered full stack comprehension. Okay, how are they measuring comprehension? I mean, yeah, it makes sense. I mean, obviously the compiler does a lot of like magic for you. All notations may need at some point to be learned by an end user, so it seems worth restricting their numbers. While notation is a tool of thought, many different notations could be a hindrance to thought. I'd say many different notations for the same thing. If you have the same notations for the same things, but then lots of different ones, it's not so much of an issue. Like category theory, right? Tries to look for ways at which things are related. So if we just relate all the similar things and like use the same notations for similar things, or the same things even, then that not only covers more bases, but also just like the issue. Like, what's an example? Like, I guess maths comes to mind. Like, I feel like the brain's quite smart. The brain doesn't struggle with learning more stuff. It's more that it struggles with learning this like similar things as if they were different, and that's the issue. Because the brain's like, because then you get confusion. Like, oh, but I want to use this symbol for this. Oh, right, no, that's the wrong thing for some reason. And like that's what your brain struggles with, as opposed to just like, oh yeah, it's a different thing. Oh yeah, I don't know this. I'll learn it. Yeah, that is something I wish that also mentioned. De-emphasizing syntax. What's that mean? It reduces implementation size at the low levels of the stack. So like less syntax, more More what? Words? De-emphasizing syntax causes source code to be closer to generated code. What kind of syntax? And the programmer's mental model to be closer to the machine, which is good. Yeah. Is it good? Is it bad? Pros and cons. Um, like that's a boolean, I guess. I'm guessing. Well, yeah, it is a boolean because it says like why do you have a boolean type if this already has a question mark? Um, the programmer is habituated to communicate precise intents and discover it in the process. Fair enough. Rather than expect the machine to make inevitably fallible assumptions. Yeah, I'm not a big fan of how compilers make assumptions. I feel like the more I feel like it's well understood that the more we can tell the compiler, the better. So that even like if it's like with type inference, for instance, even if like you don't specify the type everywhere, like every line of code, at least we have a deterministic way of informing the compiler about our type information. So that is again like it's predictable. Predictability is really important because we don't want to just make like random assumptions that we're like, why did it do that, right? Reified intention using types and tests. I see. So like a strong type system provides okay, but a strong type system is difficult if you're only using primitive types. Here there is booleans, which is good. Um, although it's weird that boolean is spelt out and int isn't. Dude, same with Java. Like, why does Java have ints but then like a boolean? Like int and bool, please, or like go one way or the other, please. Don't again like going to which point is it? This point was it? Many different notations. Like these inconsistencies is what is a hindrance to thought. Because like no needs it frustrating, but then like when you need to recall it, it's like is it bool or int or is it integer? I can't remember what's a U32. Like it's really annoying. It's really annoying, and it gets in the way of memory and just being able to code. Uh, Defines early warning of breakage, and the system is modified by outsiders. Early as in at compile time, I assume. Outsiders can't be expected to have the context of the project's development history or capabilities for thorough manual testing. Well, then why are we saying? But like, I thought the whole point was that our code is simple to understand for anyone. Forks provide an escape hatch for subcommunities of end users to bud off as their needs diverge. So yeah, good for open source stuff, right? Or that's kind of like the convenience of open source software. Deleting features they don't use to compensate for new features they do need. Tests can help divergent subcommunities continue to share features with a bounded amount of effort. Huh? Okay. Why or like how is my question for that one? But yeah, I mean this is interesting where it's like you can either have generic programming that fits all use cases, or you can have specific tools or specializations for specific cases. Um, right? Because like I guess the ultimate generic tool is like an AI that you can just throw at any problem, and it will just be able to like solve it. And like that's the ultimate generic tool. Do you want that? Like if we really care that much about generics, like if I throw like an AI, like this AI right, at like a problem that's like what's 2 plus 2? Does it really need all those resources to solve 2 plus 2? Or would I be better off, yeah, would I be better off just using like a calculator? Like even a calculator is like a lot, or just like mental like my fingers, right? Like that is the issue with generic tooling where even if you do cover many bases, there's a cost to it. And there's this growing sentiment in the programming community that's like we don't want to use what we don't need, or rather we don't want to have what we don't use. That shouldn't be weighing us down. So very, very interesting. These strategies borrow prior approaches from past work. Okay. So we had something with parsimonious dependencies that give them safety, as many languages tend to do. Small talk systems that de-emphasize safety, not really. While exposing a large fraction of their internals, cool. They usually use a kernel that requires exciting small talk to modify. Exiting, sorry. But yeah. So not like self-contained. Lisp machines built up all the way from custom hardware. Oh yeah, Lisp is cool actually. Like I talked about like the building blocks of like from basics to like abstraction. I guess Lisp kind of fits that model, except Lisp. I don't know like if Lisp first of all starts at like the lowest level of assembly machine code, and I also don't know if Lisp is particularly nice to use at higher levels of abstraction. Um, Not to mention that like if you have a language that can be built up in such a way, the way it builds up needs to be consistent as well. Um, like you don't want the C plus plus issue of having like 10 different ways to do one thing, because then you just I say 10, it's more like 10 billion, because then reading different people's code bases just becomes a pain in the ass. Um, okay, Lisp, Forth, and Smalltalk all emphasize uniform notation, though they also have strong and divergent opinions on what that notation should be, as is expected, really. While they all expose, and like that's the other thing. Like even if you create this perfect language, is it like really going to satisfy everyone's subjective opinions of what they want it to look like and like function like? Again, like even just having a language that people can use, that everyone can use, and that is accessible to everyone, is a form of making something generic, such that you're not going to satisfy specific users all the time for everything. And then that's probably why people make their own languages. That's why they use these languages that other people are like why using Java? You know, like use like Rust or C++ or like Kotlin even. But I don't know, like for their specific mindset to needs, it just happens to fit it better, which is really interesting as well. While they all expose their internals to modification in very restricted ways, it seems easy for small modifications to their internals to cause regressions, both subtle and catastrophic. Yeah, like if I change this thing like on the lower level, and then like how that propagate up to the high level of abstractions, that can cause big issues. Modification requires expertise of all the scenarios, but their environments are designed to handle. Expertise that can only be obtained out of band from the tools themselves. How do you solve this then? The Stabs project explored ways to construct a complete stack with low implementation effort. God, I'm so confused by what it means by stack in this case. Mu tries to follow in its spirit, while being more parsimonious with dependencies and notations. The work of Basman and Chenavskij, describes a mature society based on forking that we aim towards. The Steps project, you're saying? Is it energy service? No. This thing. The reinvention of programming. From atoms to life. Ooh. Okay. I want to save this then for later. I think I'll go ahead and read this. Yeah. Um, crap. How do I? God, I recently switched browsers by the way, so I need to get accustomed to this. Okay, that'll be a good video later. um, okay. Stack. Okay, please explain. Please explain. As mentioned above, Mu is parsimonious with its dependencies. Keep saying it, man. At runtime, Mu packages programs as either ELF binaries for Linux running on Linux, okay, or as bootable disk images bundled with a third-party Unix-like kernel. Okay, Mu programs don't rely on libc or any other mainstream libraries. I like it. Please just leave libc behind. We can we can we can make our own things. Come on. Eventually, we will build the OS kernel in Mu as well. Yo, what? What? Is Mu an operating system? I'm pretty confused. So you got the Mu translator written in sub X with syntax sugar. Wait a minute. Sub X. Is that what this is then? Wait, is sub X like the actual implementation of the language? What the hell? What is sub X? Huh. Sub X code. Next generation state container. Okay, I have no idea. Um, yeah, sub X with syntax sugar. Rewriter, and then without syntax sugar. Bootstrap, the translator, written C++. Is this like their... Okay, sorry, it says here. Building Mu programs, edges represent languages, so edges are their arrows, I think, while nodes, that's a tree, represent tools and indicate the language they're implemented in. Okay. Most nodes are built in the language they emit, green. Okay. Only the self-hosted translator is metacircular, red. Oh. Huh? The subx translator is written in subx. Oh, so is that what it means? So okay, so that's what it means by metacircular, where we're at a point where we're relying on the tool itself to write it to create itself. That makes sense. Okay, really, it wants to minimize that. I find that interesting because usually people want that kind of, like, I want to write the Rust compiler in Rust, or hmm. Although I can see how it creates issues, but at the same time, it, like, if you need to improve the tool with the tool, it is also a good motivation to make the tool better. And like it can expose things directly to the tool creators. The self-hosted and bootstrap translators emit identical ELF binaries given identical source programs. The clouds highlights areas that still depend on mainstream software. Okay, sure. At build time, Mu is designed to be parsimonious with its dependencies, but also easy for a newcomer to build. It can be built using two approaches. First, it can be bootstrapped on any Unix-like platform with a C and C++ compiler. Second, once a Mu machine is bootstrapped, Mu can build itself without any further reliance on C, barring the OS kernel. These two approaches have complementary strengths and weaknesses. C is relatively familiar, but C compilers have large dependency trees. Mu looks strange, but only relies on a few generic syscalls, and it's easy to audit. I mean, it's still dependent on the OS, no? But okay. Both approaches emit identical binaries. Actually, I just said that. That's quite important that it's reliant on the OS. Because then the language isn't self-contained at all. It's kind of specific. Unless you want to write different implementations for the language in different operating systems. But that's not so easy. Or well, it's not simple, that's for sure. Permitting diverse double compilation to counter the Thompson-Carger trusting trust attack. Sure, I don't know what that means. Hold on. Yeah, Zig. You know what doesn't use a C compiler? Or well, rather, what comes with Zig is interesting. Um, because it comes with its own C and C++ compiler. And like I keep hearing what's his name? The Zig, oh my god, Zig creator. Yeah, Andrew Kelly. I keep hearing Andrew Kelly say this, and people kind of just gloss over it. What do you mean Zig has his own C compiler and C++ compiler? Like, does that mean it can use it? Like, it doesn't need to rely on GCC? Because that's kind of insane. Um, wow. Anyway, kudos to Zig. Figure 1 shows the toolchain graphically and provides an overview for the rest of this paper. The Mu computing stack provides two notations: an unsafe notation for machine code, called subx. Oh, so it's subx its own thing, and a type safe and memory safe statement oriented language, eponymously called Mu. that mostly translates one-to-one to machine code. Mostly. In each rotation, we try to do as much as possible with localized rewrite rules, aka syntax sugar. So it's kind of like preferring. Hmm. So it seems like this is treating syntax sugar as not an abstraction, which is interesting. More like a convenience kind of thing. Okay, the 32 bits bedrock, yeah. Yes, currently Mu supports only the Intel x86 instruction set. Portability is explicitly a non-goal. Portability guarantees require extra effort to maintain and can be particularly challenging for newcomers who may not be inclined to ensure their changes work on platforms that you don't regularly run. Rather than attempt to fight a losing battle, we retreat from it entirely. Ooh, what? I mean, I get it for Mu, but like for the sake of a bigger scope project, you would definitely need to have some kind of like at least like an approach to get that to go. Sorry, hold on. Non-goal speed. Man, this is okay. This paper and language is interesting, but I feel like it's not like it hasn't defined itself properly. Um, like speed clearly is a goal, or like at least it's like it's not a non-goal. It's more like a goal that's already been satisfied. Because obviously people want speed, efficiency, controlling the number of instructions could should manually keep. Again, like it just naturally solves the goal, but that doesn't mean it isn't a goal. Portability, as you just read, Mu will run on any computer as long as it's x86 32-bit. I will enthusiastically contribute to support for other processors in separate forks. Interesting. Again, forking over generic. A reader shouldn't have to think about processors they don't have. I mean, they usually don't anyway. Like, if someone doesn't care about a software working for other people, then they'll just go with, wow, they'll just say it works with my machine. But I guess the idea is that you want to make tools that only you will use, and therefore, again, you don't want to pay for what you don't use, right? So again, like just that would be a clearer way to word that, assuming that is what this is getting at. Compatibility and syntax. Mu code is meant to be comprehended by running, not just reading. Huh? It will always be just a thin memory-safe veneer of machine code. I don't know how to make higher-level notations both fast and comprehensible, so they are likely to remain slow and incomprehensible. Useful for prototyping, but invariably needing to be rewritten in statements that map one-to-one with machine code. Hmm. I mean, at least it's honest. I don't know, but like, we should try, man. Nobody's just reading your code. Shiza. I'm just gonna quickly skim through this because I think I need a bit more context about this project. So most programmers agree that we don't read enough code. Uh, Read students' code. If you go to Google, a nice print out and read it. Why would you read code? Like for like as like a leisurely activity though. Like unless you specifically want to improve your thing. Like it's like reading I don't know, like for me, like learning Spanish. If I read articles in Spanish, that obviously help me improve my Spanish. But like if I don't care about what I'm actually reading, then that's really forced. And honestly, I don't even think I don't even think it's that effective because like motivation is a key part of learning. Um, like you need a motivation to read code, don't you? Learning code through hacking, yeah, actually, yeah, game hacking is a good way to do that. Contributing to open source software is also really good for reading code, having a reason for it. Okay, I'm not even sure what this is. getting at. Same site, by the way. Anyway, I just closed Moo. Whoops. Um, Moo supports only a regular subset of the entire x86 instruction set, mostly restricting itself to 32-bit instructions that have been widely available since 1990. Since they also only rely on a bare minimum of features from the OS kernel, MIB programs should be easy to get up and running on any computer people have access to. Okay. Only have support for integer operations, because floating point is obviously non-standard. But yeah, at the same time, interpreting signed integers is not standard either. I mean, it's been standardized, but like just generally speaking, there's one way to do it. Uh, 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 uh okay. The lowest levels are our goal is to come up with a reasonably ergonomic syntax that can be implemented in itself. Okay, so they want that metacircular dependency. Given this hard constraint, we don't try to be abstract over the underlying machine. Programmers working at this level are exposed to the constraints and complexities of the instruction sets, given that it's worth taking some time to talk of it. Like, this is kind of just seems to me like the language is kind of just then assembly with syntax sugar. Like, literally, what's the difference? Because it's specific to only x86 32-bit. It's specific to Unix, or like some specific Unix, I don't know. And if you want to make your own, you need to kind of make your own implementation. And then they're avoiding abstraction. Yeah, like how is this different from just assembly with syntactic sugar? Okay. Um, it's explaining how 32-bit registers and commands work. Yeah, like we're just explaining what x86 is now. I do wonder what by the way, like what the motivation for this thing was. Like, was this just someone doing it for fun, or like were they doing it to like for some like university or like master's dissertation? Like, what? Why? This just seems very bizarre to me because like it has this idea, which I think is cool, but like the way it goes about it seems very unambitious and very just like let's just do assembly, but nicer looking. Like, fair enough, but then why make a whole paper about it? I'm very confused. Subx, how to build notation for programming in machine code. Okay, at this point, it's worth taking a step back to think about why we don't all program in machine code. Let's go. At least in place of unsafe languages. Right, so safety aside. Ignoring aesthetics. Okay, but like we need to, guys, we need to address aesthetics. Humans are not machines. Humans are not robots. We write code for robots, but we still need to be able to actually reason about our code and think about it and not, kill ourselves over it. There are some essential difficulties. Non-textual data is not a good fit for human senses. Very true. Packing bits into machine code, not even assembly. Packing bits into bytes is error prone. What you mean? A variable like what? Like writing out bits by hand, you mean? And then making sure they fit bytes? Like 8-bit alignment, for instance? I don't know. A variable instruction set requires path-dependent encoding. Small errors in one instruction can cause later opcodes to suddenly be interpreted as arguments and vice versa. Errors may manifest unboundedly far from their root causes, making diagnosis intractable. Mm-hmm. Yep. Computing offsets. I mean, yeah, it's like, sorry, this is a big issue with, like, again, like the building block idea I have, or that I proposed, whatever that I talked about. Like if Rust, for instance, I keep saying Rust, but I think Rust is a really just a really nice high level language. Whether or not you think it's like the most efficient, like the most perfect for like yeah, like efficient software. I would say at least that, like in terms of mental modeling and just writing code that you can understand, Rust does a great job. Um, Not perfect, but still. That's why I keep using it as an example. And if you were to like kind of like do this building blocks approach with something like Rust, like yeah, like if you make a mistake at the low level, the effect that would have at a high level is just so huge. And it's easier to implement high level code in other high level code, if that makes sense. Like let's say I'm designing iterators. Like I guess I need to use like a for loop, but then I also need to like implement the for loop. Um, and it's easier if I can just use like some other language like C or like whatever that already has it built in, because then like I know it's less error prone. Use it like the LLVM intermediate language, because then like that's reliable. So I guess what I'm trying to say is the main issue with the building blocks approach isn't necessarily that everything can just fall down. Like that's kind of a given for any software. Um, because you can make mistakes at any level and whatever. Like that's normal. But it's more that it means that everything has to be written in the same language, which seems good until you consider that modular design is so important as well at big scale projects, large scale projects. Like the reason that Rust relies, I mean, I believe it does, relies, I mean, yeah, the last time I checked, Rust does still rely on the LLVM IR. And then like it uses LLVM for optimizations and stuff like that. Obviously, the Clang for C++ does. I think Zig might, although Zig might either have moved away from it or is planning to, if I remember correctly. But like the good thing about that is that people who work at LVM then can, like you can just trust that the people working at LVM will make it working, and then if there are any issues, then you can fix it yourself. You can learn how it works as well, LVM, and then you can fix it. And then not only does that fix your tool, but then it also fixes and benefits other tools, right? So like in that case, having like these this modular design is quite cool, quite important. Um, Whereas if you were to like have everything be self-contained, then not only do other people benefit less from it, but it also means that they that you are going to struggle to find people to help you. Because like there is like a resource problem of like, well, if your thing is coded in your own language and people don't already like your language, then why would they contribute to it? Whereas if they have this thing that everyone depends on, then people that there's more motivation to make sure it's actually good. So that's another interesting thing that I think holds back this idea of just building it up from the ground up. Um, but then of course, like if again like LLVM has an issue and you don't know how LVM works, then you have a problem there and you're at the mercy of them to fix it. So there's it goes both ways, like pros and cons again. Computing offsets for jumps is error prone. Yep, because for like addresses you have to do it yourself. Whereas if the compiler can keep track of that itself, then that's obviously much better because you can just give it a unique name and refer to it by name. Naming things, man, humans and naming is just such a huge part of human abstraction. And then various other error conditions can yield terse or cryptic results. Because I guess so. Because like I guess the idea here is that if you write machine code by hand, like if you make a typo, good luck. Like you have to be so careful. Given our tight complexity budget for self-conscious syntax, these difficulties are our top priorities. To begin, we follow a long tradition and write programs in a hexadecimal representation of ASCII bytes. Yikes! Converting them to binary before running them. What? Hexadecimal representation of ASCII bytes. You don't really need to convert them to binary though, unless you're writing them like as text. But like if you just use like a hex editor, then it's automatically already binary encoded anyway. The rest of the stack can now work with programs as textual representations of numbers. Sure. It says textual, so okay. Metadata. While machine code consists of undifferentiated numbers, mixing in some redundant information can help improve the quality and timeliness of errors. Conventional assembly languages do so by creating mnemonics for opcodes and translating mnemonics and operands into machine code. Yep, you have your MOV EAX 3,3. However, assembly mnemonics can often expand to multiple opcodes depending on the arguments. That is true. Wow, so it actually they're trying to say it wants to go lower level than assembly, or like less even more explicit. That's interesting, honestly. For example, assemblers translating opcodes can also convolute the logic for good error messages. I guess. For example, assemblers may need to inform the programmer that there's just no instruction in x86 to multiply ECX by EDX. Yeah, okay. For easy translation and simple but robust error messages, we work with numbers directly, but append metadata to them after a slash. Here are some example instructions in subx illustrating the simple and the complex. C3/return. Yeah, so I saw this, right? It's an idea. Holy moly. Holy moly. Instructions always occur one to a line. Yeah, just an aside here. And actually, while I make this video, I should also note down some ideas this gives me. Um, I've got my blog ideas over here. um, little sneak peeks there. I've already made one of these. Yeah, I made this one already, so I can delete that. But like one thing I wonder about is white space versus semicolon. Because like people generally say they hate white space in programming, but like if you look at I'm not saying that assembly is like the gold standard for an ergonomic programming language, but like just notice that assembly doesn't even have it. Sorry, semicolons. Jesus Christ, assembly does use new lines to separate statements. Like, isn't that interesting? Do we need semicolons? Um. Anyway, in the first instructions, the metadata is only the numbers at the start of each word represent a computation encoded in the final binary. Right, so I've like 0, okay? The rest of each word is metadata. In the first two instructions, the metadata is relatively easy to read. Okay? And so what's going on here? So are these lines here? So return C3. Which C3 being, I assume, a hex number? As opposed to a decimal. 68, so push 68, and then whatever this instruction is, I guess, 4. Is that float? Jump if lesser. Copy mod. What the hell is going on here? In the first instructions, okay, the third example, this one, demonstrates an instruction with multiple opcodes. These opcodes. Oh, okay. So these are opcodes. I'm guessing then. So the first one is just return. The second one then is push with this opcode. I'm guessing. Yeah. I mean, if I knew x86 assembly better, I would be able to read this more. The third example demonstrates an instruction with multiple opcodes. Fourth example looks at memory and adjusts in ECX and saves results to EAX. So it's a copy. Oh, okay. So it's 8B copy. So C3 is like is the hexadecimal representation of these commands. So like 68 is push. Okay. I understand that. So like 1 is ECX and 0 is AX. RM32, R32. Like register 32-bit? Yeah, okay. The sub X translator ignores unrecognized metadata. So this is sub X. Ignores unrecognized metadata as opposed to erroring it. In the above examples, return, push, and ECX are just comments for human readers. Okay. However, metadata can also affect translation by labeling arguments to be processed in different ways. Man, this is interesting. Because my issue was looking at the Muth language is that they had lots of these like redundant things. Um, but if they're like effectively just comments, I understand, but I don't necessarily agree that that's useful. As the sub-X translator processes up, I can't speak today. As the sub-X translator processes opcodes, I'm getting really congested. It checks for expected argument to labels. For example, it expects the opcode 68 push to provide a single argument and for that argument to be labeled with IMM32. Any discrepancies are immediately flagged as translation errors. Good. In more complex instructions, metadata also permits the sub-X translator to perform the tedious task of packing bit fields into bytes. Okay. Okay. So we got labels, string literals, tests. Tests are an essential component of programming in machine code using sub-X. Kojo generated program. When it calls all functions in the program. So it's kind of like, compile time testing. It's cool. I like it. Tests are partially essential when programming, particularly essential when programming in machine code because there's no task so simple that I get it right the first time. now it mentions this. Um, sure, but why not? Okay. So is this yeah? So this is the what's it called again? Sub X language. God damn! You're telling me that this is easier to write than assembly, like like x86 assembler. NASM, sorry, is what I meant, or even like GCC, whatever that has for it, or GNU even. Sorry, GNU assembly. Bro, what the hell? I see the vision, but like the fact you need to also like memorize these, like why can't those just be labeled? I really don't understand why this is useful. But like these numbers are just magic numbers anyway. So having a lookup table for what they correspond to is just better, especially if the compiler already checks that they match as well. Call factorial, and like why like factorial is a label, so like why are we saying that labels? I mean, it said up above about labels, but like why then? Why do we draw the line at like the names of these things? Okay, okay. Hex converts hexadecimal bytes into a binary file. C++ translator. I see. Debugging. Sure. Syntax sugar. Yeah, we give up a lot of syntactic ergonomics when using subx. Now that we have a baseline that satisfies the implementation properties we care about. Huh? Yeah, I don't understand the. I mean, I guess I'm guessing it goes into detail of like why they do. Well, not really. Like it didn't really explain why we do this. Like how's this useful? I don't understand. I don't understand. This is really confusing me. What like some of these decisions are really confusing me because it's not really explained. Um. Okay. Emulation. The final bit of syntax trigger that seems to provide a high power to a ratio is the elimination of unstructured jumps in favor of structured conditionals and loops. Welcome to C. Assembly languages either don't provide syntax for structured control flow, or carve out exceptions to their statement-oriented nature to support recursive syntax. SubX does neither, but instead supports assembler syntax that stick to the statement-oriented nature of the underlying machine. So, I see. So instead of this, we have this. Fair enough. Okay, like, what the hell? Like, I'm not, again, I don't fully understand what SubX is for. Like, if Mu exists, why are we making two languages here? Also, sorry, the title of the paper, bicycles for the mind have to be see-through. So if you have a bicycle in your mind, as what's his name, Steve Jobs was saying, then the argument here is that you need to be able to see the bicycle. But like people who ride a bicycle don't necessarily understand how a bicycle works. Um, okay, let's move on to the move here. So SubX helps us minimize dependencies on mainstream software. Yeah, but can't you do the same thing for Mu? Just like make Mu pilot itself. In this section, we describe how we build on SubX to obtain a memory safe language Mu. So from my understanding, sorry, since we now have a fairly habitable notation, we can expand our ambitions a bit. However, we're still fairly parsimonious in the features we introduce since the implementation language is unsafe. So, like, is the only reason to have SubX just that it's unsafe? So, like, does that mean that Mu is limited in some ways? Mu's trajectory follows that of early C to some extent. Yeah, you don't say. Both languages were implemented without a high-level language, and so implementation simplicity was important. However, Mu learns from the trajectory of C, where compilers became metacircular at the first opportunity. Why is that bad, man? Like, it hasn't explained why it's bad, man. Like, we need some more reasoning behind these decisions because right now they definitely go against what people have tested already, and you got to elaborate on why. I'm very confused. However, Mu learns how, and the availability of a high-level language for implementation has caused ever smarter compilers at the cost of explosive growth in compiler complexity. We don't want to make the same trade-off. Fine. To avoid ever needing a complex compiler, good. I agree with this. Mu is designed to never need any compiler optimizations. Right. I have another idea for a blog post, which is it possible to have a programming language without need of compiler optimization? And also a language that builds itself from the ground up. From the ground, machine code, up. Yeah. These are very interesting topics I want to get into. To avoid, yep. It achieves its aim by staying as close to the machine as possible without compromising memory safety. In particular, I think in that case, the most interesting thing about this language is the fact that it supposedly achieves memory safety while still being extremely low level. In particular, we aim as far as possible for each statement of safe mu to expand to a single instruction of unsafe subx. Okay. One consequence of aspiring to a one-to-one mapping with machine code, we don't abstract away registers. Yeah, but you don't like that? Since x86 machine code constrains instructions to no more than one memory operand, it makes sense to make programmers manage registers explicitly. We'll still verify the register allocation as described below. Okay. Do they also have to then manage to stack? I assume no, because that can be automated. But yeah, using registers isn't so bad. Like C has support for like registers that you can specify. Well, it's not even true. Like C has or well, it had. I don't know if it's been deprecated, but like it had the register keyword, which let you say to put something in a register, but not so much which specific register. Um, the reason being that it is deprecated because a compiler can just reason about that much better than a human can. Like to manually keep track of registers is just so much mental overhead that it's really like it makes it hard to do a lot. And I'm again I'm just amazed that what's it called, Roller Coaster Tycoon was able to be made. Like I need to look at that source code sometime because goddamn impressive. Figure 8 shows a small example program in the safe language mode. Where? Here. Okay. So we have a type point, which is xy. Um, there we go. We have a function called higher with a point, b point. So these are the arguments. Interestingly, we don't specify the registers the arguments go into, but I can only assume that that's because it's by default ECX and EDX. But then why is this EAX? Or maybe they're stack arguments. Also, these don't have a. Oh no, the type is points. Okay. Trailing return type. There's no separation of these, but that's whatever. That's I guess a personal issue. Results. Oh yeah, I found this interesting actually. That you can define the return value initially. Because like regardless, you'll need to return something unless you like even if the return type is void. I believe every call to a function still expects EAX to contain the value if it exists. So I don't understand why we need to specify EAX here. I wonder if that's ever different, and I also wonder how cool, how useful it would be if other languages gave you this kind of variable. Um, so languages, so return type and name. Yeah, yeah, a bit cryptic, but I know what I mean. Because then you can just like you can assign to the return directly, and then return. I mean, I guess it does it here, right? Return copy AY, so it's moving that into that, and then it's returning, which is different than just like returning a value, like return 5, right? Um, because it doesn't mean you need to assign to the output. So I guess having an option would be useful. Hmm. I'll definitely come back to that and expand on those thoughts. Var, declare a variable, AY, int. So I assume that then allocates on the stack. We move, oh, get a Y. Okay, so we get Y from A, because A is a point. Man, goddamn, ooh. So, okay, if this is like deeply nested, like a point within a circle within a shape type, not recursive, but like, how does that even, I really wonder how that would work. Then AY. Also, like get is so, man, like these languages, like they want to be like assembly, but then like be a bit simpler, like easier to understand. But then like how is get easier to understand? If it was like get child, that would already be a better name. But even then, just like a.y is pretty eh, intuitive. But fine, we're moving a.y into ay, and then we're creating a variable by, but this will be an eax. Sure. which is the same. So that's already conflicting with this. But fine. Then we move b dot y into EAX. And then we compare AY and BY. Break if less than or equal to. So if it's less than or equal to, it will just not do this. Which means it's checking if A is more than Y. If AY is more than BY. If it is, then copy AY into results. Otherwise, copy BY into results. Okay, it's a mistake. Why do they both use EAX? Like, why are we copying if it's already in EAX? I don't know. Okay. Figure 8 shows a small example program in the same language sorry. Just like in C programs. Just like in C, programs are sequences of function type and global variable declarations. They may specify a register. Variables not in a register will be placed in memory. In memory? Okay, I assume it means like RAM. So is that on the stack? It must be. Figure 8 illustrates a few constraints, mostly imposed by the x86 processor. Functions must always give their arguments on the stack, and must always return results in registers. Oh, okay. Really? I thought x86 could also have arguments in the ECX and EDX registers. Like for the fast call convention, which is now the standard for 64 bits, the first two arguments always go, well, I think they always go to RCX and RDX. But okay. Um, the registers they return the results in are part of their signature, and every call must conform to such constraints. So, but again, like, isn't it always EAX? Like, kind of, like I know, I know you don't want to hide it, right? Like, why? Why not? What are we losing? Like, genuinely, what are we losing? Like, just read somewhere that says the return type is always an EAX, and then like you just know it, and then you don't have to like write it out every single time. Hmm. Like, a lot here seems kind of counterintuitive. The registers they return the results in. Some primitives, such as get, can return results in an arbitrary registers. No primitive can operate on more than one variable in memory. Remaining operands must be in registers. We have special instructions for accessing members of records and arrays. Uh, oh my god. Even though they may translate to the same opcodes under the hood, giving them separate names helps document intention and enforce type correctness. I see. Okay, that's fair enough. That is fair enough. Conversely, the compare dude, like I love this reasoning. Conversely, the compare instruction translates to different opcodes depending on whether the second instruction lies in memory. Why? Like, how do you justify this? We continue to use sub-X's scheme for structured control flow, break and loop. Um, okay. Yeah. I'm very confused. Like a lot of these decisions seem to kind of conflict with each other. Like they don't like they're not consistent with each other. Like why? Like okay, fine. We want to use different words for get and whatever for intention, but then for compare, we're going to have them translate to different opcodes depending on the thing, like depending on whatever the thing is, whatever the right. Because like the same compare opcode can't be used for different, like if one's in memory, one's in a register. I don't know, whatever. Fine, because like that's intention, that's fine. But then why? But like then do we not care about the low level process then? Like do we just not care? Like we just ignore it? We just abstract it away like a black box? Like this seems very against the ethos or the goal of this project, and it seems like that by implementing this, we're kind of realizing, you know what? Let's just actually get rid of this and get rid of that. And you know what? Maybe high level languages aren't so bad after all. Type system. I love type systems, or like I love reading about them. Mu has a strong but unambitious. Yeah, wow. Okay, type system. The only goal is to avoid the memory corruption issues that plague the level below. Type checking happens in a pass between parsing and code generation, and for the most part consists of matching types between the left and the right hand of instructions. Yep. Hammer conversions. When the instruction is a function call, the type checker takes the function. Yeah. So it checks the signatures of the functions, and then yep. Makes sense. Pretty basic. Individual instructions impose their own constraints. Um, Mu enforces that the add construction can only operate and yield in values. Yeah, are there fixed width integers? I haven't seen any yet. The index instruction always performs bounds checking at runtime. This constitutes an exception where a mu statement requires more than one subject instruction to implement. So it's not one to one basically. Okay, but like, are there like implications to these exceptions? Like, if we need to make exceptions, then maybe our module just wasn't really logical in the first place. Types can be compound, and we express them as expressions. For example, array int. Okay, fine. An index instruction on a variable of type array point gives an output of type point, like an array of integers, an array of points. Yeah, okay. Um, Makes sense. So then, like, it can like unwrap them, I guess, to get the type information inside. Mu will have some types, will have, or tagged unions. Some superficial syntactic details remain to be finalized. I really wonder how they are going to do that, because that is like, like if we talk about hiding implementation details, tagged unions like in Rust, like you can make them in C, but like for them to really be convenient, there's a lot you need to kind of abstract away. Um, I really need to look into Zig, honestly, because like I know Zig cares a lot about data oriented design, um, and I suspect that Zig will also contradict his own goals in similar ways that like I see this one doing it. So I'm very curious. Um, anyway, we're also trying to integrate Kalen style, have you pronounced that, anonymous union types like int or error. Okay, where error is like an enum, I'm guessing. Did it? Yeah, does it have enums actually? Sub x creates a space for local variables using push instructions. Oh, yeah. So variable image register on stack. Okay, yeah. So as I thought, the stack is default. So you don't need to specify the stack position or anything. You just put it there. How a heap then? How do you allocate the heap? In the safe language, we disallow the push and pop instructions, as well as the direct access to the ESP and EVP pointers. Oh, okay, so there's also memory safety involved in that, which makes sense. Really? So, yeah, I kind of forgot the whole memory safety thing. So, like, if you need to hide the stack operations, or like at least like abstract them away, in order to have memory safety, how does this work with registers then? Like, do you like if ESP and EVP are so problematic? I mean, of course they are because you don't have to like you don't want to mess it up. Um, are the other registers safer? I wonder. Um, yeah. So it's scoped with these. Um, I talked earlier about white space versus semicolons and stuff. I do think that the braces are actually important for scope. So even though like we don't necessarily need to have semicolons, having braces for scope is quite useful. But then again, like we don't need to have braces around like if statements. Like we can keep braces for those specific cases where we want scope, or even we can have like a keyword like scope, for like just scope like that, and then like and then anything under that indentation is scoped. Anyway, so yeah, variable in stack, variable in register must be initialized with a valid instruction because it's just an alias, an alias for the stack. So like if I can have var x on EAX and var y on EAX, then they both point to the same address, which I feel like is can cause memory safety issues. But like at this level, like what's even considered a memory safety violation? Like crashing, I guess, accessing out of bounds memory. Like I guess so, but like there are other ways that you can make memory issues that are more like the programmer's fault. I mean, they're all the programmer's fault, but I mean like just other ways to just cause issues. I don't know. All variable declarations automatically initialize their underlying memory at runtime. Arrays and strings are prefixed with length, and automatically reclaim it when exiting their block. Okay, and there's an exception. Addresses. He mentioned in Moo we try to separate these intentions. So there's an address and a handle. Okay. Two different address types. Now that is new to me. Function arguments with type address indicate call by reference. Right, so you pass the address. Okay. Figure 9 shows that figure 8 would be modified to accept its argument by reference. So that's here. In brackets, address point, address point. Fair enough. They are not going to use a special symbol for that, but honestly, fair, I guess. Values of type address are intended to be short-lived. They cannot be saved inside user-defined types. Ooh, to preserve safety, mood tracks functions that could reclaim memory and raises an error if an address variable's lifetime intersects with any memory reclamation. Ooh, okay. Hold on, chat. Go. This is interesting. This is interesting. So, because passing my address is just kind of just a way to not have to copy. But like, if you store it in a struct, is it not the same thing? A more complex transition variables and control flow. Where does it mention figure 10? I don't know. Let's look at it anyway. So if we had a var EAX, well, var x and EAX with an int, and we want to copy 0 into it, instead we... Huh? Huh? Okay. I'm assuming, is this Moo still? Or is this the other language, sub x? But yeah, it pushes EAX, and then it copies the EAX 0, jump if equal, and then pops it at the end of the scope. Okay, fine. The second address type is the handle. It is a result of a heap allocation. Okay. The issue with this is, what if I want a custom allocator? It's the only kind of address that can be saved inside a user. Okay. Handles are fat pointers. They includes nice. They include an allocation ID that is also present in their payload. Handles can't access their payload directly. They must first be converted to an address using the lookup instruction. The lookup instruction constitutes the third and final exception. Sure. On every lookup instruction, Moo compares at runtime the allocation ID of the handle with the allocation ID of the underlying payload. A mismatch in allocation ID indicates an attempt to access memory that's been reclaimed. Aborting immediately on an attempt to corrupt memory prevents many security vulnerabilities. Interesting. Interesting. This sounds very similar to the borrow checker, does it not? Because we're checking ownership, aren't we? We're checking who owns it. Like this lookup thing, where we compare the allocation ID with the other ID. Except this is runtime. Yeah, what the hell? What? Is this memory safe if it's a runtime exception? Like it still crashes the program. Yeah, okay. Um, yeah, but anyway, it's I forgot who the YouTuber is, but he made a point about how annoying C++'s address pass by references. Like he makes a good point where it's actually probably better to pass by pointers explicitly. So let me create a. Actually, I'll just launch a new Vim directly. Like if I have a program like a function, I don't know, goddamn. Okay, void prints, right? And then I have, let's zoom in here. I take a string, for instance, or we'll do like this, string a or stir foo. I'm not gonna worry too much about the specifics. And then like we just I don't know, something like this, right? You can either pass by reference or you could pass by pointer. And passing by reference in C++ is pretty much just syntactic sugar. So if I have my code that's like print um something like this. I mean, this isn't C++. I'm just kind of giving an example in general. Like this here implicitly passes by reference. Whereas if I explicitly pass by pointer, it's the exact same thing. The only difference is that now I have this, and then I need to then dereference this. So it's syntactic sugar. And I agree that passing by reference, while convenient, is really like it doesn't help here. I don't know. There's a lot more to say about this because like if we care about making this explicit, what else do we care about being explicit in the function call? Like, oh, no, I think we should also make the name explicit, you know? And I think we should actually make the type explicit as well, you know? And like I think we should even make it more explicit that the thing returns void, you know? It's like, okay, like where do we draw the line? Um, and anyway, I mentioned this because like fat pointers exist, but how about fat addresses? I don't know, man. Like a fat address would just be a fat pointer, I guess. Because like if passing by reference is just syntactic sugar for passing by well address, but like it's a pointer, then having a fat pointer necessitates the existence of a fat pass by reference. I think if that makes sense. And then for Rust, you do need to make it explicit, right? That you're passing by reference, because I think by default, I think copying is the default. No, moving is a default in Rust, whereas copying is a default in C++. And because moving is a default in Rust, you need to pass by reference if you want to pass by reference, right? Because the only other way that you could pass it is to dot copy it to make it explicit, or like dot clone. Yeah. Anyway, I'm fairly new to Rust, but it's an interesting model. Okay, then scope. Okay. Uh, I'm gonna skip the rest of this. Reifying intention. We have a stack that fits in a single person's head. Yeah, for small function it does. Maybe. But like guys, it just doesn't scale. It's not yet a fair comparison with mainstream software because all software starts out small and simple. Ah, look at that. We wouldn't want to pit the quality of Mu against that of early C and Unix implementations. Might Mu to grow bloated and complex over say a decade, particularly in the unlikely event it achieves significant adoption. Yes, complexity often stems from the arrival of newcomers and the gradual forgetting of the causes for design. Why is this referenced? Like, are these quotes? Or are these like people studies? I'm very confused. Um, hmm. Like, okay, this section describes some pervasive mechanisms and the implementation of Mu to combat complexity creep over time, and to educate people about rationales at all levels of the stack. So there seems to be like a big want for people to understand what's going on, right? Because if they understand the system better, then they can better use it. If you understand the tool, you can most effectively use the tool, which is, I mean, I agree with, and I really wonder how that can be implemented in a good way, because this is not really a great way. One source of complexity in mainstream software is the usage of syntax. New notations are often marketed in a dead form, like a web page or book, huh? Where one must judge them by how they look, without interacting with them in any way. The need for such marketing in turn drives the design of server syntax. I think much of this pursuit is misguided. Design effort spent on server syntax comes at the expense of other considerations. Non-leaky abstractions. What is a leaky abstraction? Syntax creates greater impedance mismatch between the interface exposed and the work done for the programmer. I don't really understand what this is saying. Min explores a contrary approach. It's designed from the ground up to minimize impedance mismatch at all levels. We front load education to optimize for the long term rather than the initial experience. So yeah, like more boilerplate now for easier code later. Which again, like with the example I gave, if we specified like the variable, like the arguments, function type names, and their variables, so that like you don't need an LSP to tell you what the signature is. But then like you have more boilerplates, but like it makes reading really easy. It is a very, 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 very interesting argument. Like, like good boilerplates makes reading easier. Should we have boilerplates? And I think personally, the answer just comes down to how much can we rely on automation as well. Like, if we can just assume that everyone has an LSP that will tell them the type of a variable, sorry, like the type signature of a function or the type of a variable, then fair enough. That means we can just not do that. But like, what if you don't have an LSP then? Right? You kind of left in the dirt. Um, so we need to really then make sure that these LSPs are as accessible as possible. um, I still don't have an LSP installed with my NeoVim. I need to set that up. But yeah, I don't know. Or things like function argument names. Um, like some IDEs I know, like they will show you the function names. Like I think Visual Studio can do it, and VS Code might be able to do it with like extensions. But like clearly it's not standard either. So I think yeah, I think we need to kind of focus more on that as well when designing languages, where if we don't encode useful information somewhere and we are going to rely on the LSP to encode that information and give it to the programmer, sorry, like not encode, but like just present it to the programmer, then we need to make sure that is happening. Otherwise, there's just an issue with confusion. 'Cause, like yeah, Mu explores a contrary approach. It's designed from the ground up. I just read this. Okay. So Alex requires opcodes rather than mnemonics. They are so yeah. I mean, mnemonics look like English words and are therefore friendly at first glance. Natural language is often misleading when applied to programming. Often, the instruction "and" has many sharp edges in assembly language that the English word fails to encompass. Okay, no, this is fair. They hypothesize that if they just use explicit opcode names or even just like IDs, like numbers, then you don't need to worry about the English understanding getting in the way of the actual what's happening. And this is a very interesting problem, right? I mean, like right now, I can open a new tab open my console. Actually, that's a terrible idea. I might like leak some private information. Let's do this. Let's do Python online. Let's see if this actually runs first of all. Great. Like, look at this, right? Let me just change this so it doesn't require int. I have some, right? Let's change this to add. I mean, this is a classic example. Let's run it. I can do 3 and 5, and we get 35. Why? Because this is a string. And add a plus b can also add two strings. And because we have not specified a type here, then that just works, right? Or if we look at JavaScript, well, what the hell? Let's say we have again, oh my god, how does JavaScript work? I think like this, a, b, return a plus b. Is that valid? Like if I want to add 3 and 5, I have 8. Let's add hello and world. Like this stuff, this function just does this. And these are both conceptually like two ways to add. Like you can add or you can like add, but like they both just work. And I don't know if this is even like an intentional JavaScript an intentional thing that JavaScript and Python added, or if it's more just like the result of abstraction of like we have this plus operator and it can do different things depending on the types, and the consequence of that is that we can have stuff like this where we have adds just does two completely different things. Whereas of course if we specified the type signature, what? How do you specify type? Can you? You have to add it like this. But this still works. So like it's a suggestion at best. Man, JavaScript is cooked. But like just like the type system is cooked. But yeah, I do agree with this. But I feel like just like resorting to really cryptic names isn't the best solution either. I think we can find a good middle ground. Movement subjects are statement oriented and provide minimal syntax, so that translation steps are tractable to present okay. People are constantly encouraged to browse large traces using the packagable UI. Okay. Any high-level expression-oriented language builds top Mu. Expression-oriented language. Yo. Wait, what? What's that? Like Haskell? Like functional-oriented programming? We'll need a lot more work to preserve this sense of transparency while performing more complex transformations on user code. Okay, sure. Initial experience is promising. I don't know. It's very tedious to write. Like from what I'm seeing so far, Mu is quite tedious to write, and like the overhead is there, even at a small scale. Like do Fizzbuzz or something, where modern compilers grow more complex and so need to manage more safer error messages, which in turn cause greater complexity. Mu shows that transparent implementations can cause people to understand details, and so requires simpler error messages. That's true. If the programmer understands more about what a function is doing, then like it doesn't need like if a programmer if a programmer understands that dividing by zero is an error, right? Like it's undefined. Then if they see like then the error message can just say, "Yo, look at line 19. You are doing 5 divided by 0." and then the programmer will say, oh yeah, okay, and divided by zero, as opposed to the error message saying division by zero on line 17. Um, but even then, like I know it's simpler to just like simpler for the implementation to not have to say division by zero and just say look at this line. But why not make it clearer either by just saying division by zero? I don't know. I don't know. Anyway, testable interfaces. Okay. White box tests. Charging forks. Okay, let's look at the summary then. I'm more certain of this section than any other in this paper. Damn. Even if Moo's specific architectural choices turn out to be wrong, the mechanisms of forks, traces, abstraction-friendly OS interfaces, and abstraction-hostile error messages seem compelling for Illich's agenda of promoting conviviality and managing the complexity of our software supply chains. Yeah, I don't know, man. I don't know. I think it's not so. Like, these are all things on paper, but like to actually implement them, we need to like really like programmers as a community need to come together and like really just focus on these and get them down, right? Like, okay, well, let me read the conclusion before I give my final thoughts. Among programmers, sorry, before I built a wall, I'd ask to know what I was walling in or walling out. Fine. Among programmers, there's a long-standing lament about the excessive complexity in software projects. Of course, we will always complain. For good reason, I mean. Ivan Illich points out that this tendency towards complexity isn't restricted to software, but rather stems from socio-political causes, the need to structure society with certain specialization and compatibility constraints. Yeah, ice cream truck. That's why I love software, because it just applies, like, the ideas in software and good software apply to just systems in general, and they're so important for society and things in general, you know? Given these constraints, Conway's law, like Connor's Game of Life, takes over. The complexity of our software infrastructure largely reflects to the complexity in our social arrangements. The original sin is to try to decompose a system into an inside and an outside. Damn, a sin. While the instinct is laudable, it invariably leads to specialization, repeated over and over, and the number of such boundaries compounds, constraining us all. What is to be done? Mu attempts a high-risk maneuver I think of as Conway's law in reverse. We stubbornly refuse to provide the usual dichotomies of inside versus outside, and by this means hope the benefits of this approach, if they exist, cause society to consider it, with a very slow cascade of consequences resulting in a competing social arrangement. What the hell? That's a lot of words, man. That just kind of go together. What I take away from this, like the inside and outside, I think about private and public access in like classes and stuff. Specifically in object-oriented programming, but also like in module-oriented programming, which is like kind of just class. I mean, like modules are kind of very similar to classes anyway, but you can choose what to export and what to expose to the programmer. And some people would actually argue that you keep everything public, but I would argue that like for the sake of a simple interface and like not confusing users, you do want to hide stuff sometimes, and by sometimes I mean often. This paper has demonstrated okay. So some ways in which Mu deconstructs the dichotomy between inside and outside are by selecting notations at the lowest level for implementation properties. Okay. Yeah. Again, I don't understand what it says about my notation. I still don't understand what it means by notations. When I think of notations, I think of like I don't know, using like square brackets for arrays or whatever. By using traces to show details rather than modules to hide details. Okay, I didn't look too deeply into what traces are, but I might look into that later then. By making tests white box rather than black box. I saw that up above. I didn't look into it though. By encouraging the distribution of whole computers rather than the packages. Do you want that? By encouraging users to fork open source software rather than submit to a centralized governance process. Yeah. Although that can cause efforts to kind of spread thin, and then things don't really like it. In some ways, it defeats the purpose of open source software because like we're not really giving back to the source. So like the benefits are very individual as opposed to more collectivist, you know? By optimizing for learnability rather than familiarity. So it's easier to learn than it is to be familiar with. In the process, we've taken on some big risks. Taken on some risks. Many programs are aesthetically unappealing. Debugging may be hard with this approach. Debugging is so important though that like we really cannot skip past the importance of debugging. If you cannot debug your code easily, the language is just like that's like well that might be the single biggest factor. Besides like the power of the language, like what it can and can't do. If you can't debug it easily, like that's probably the biggest thing that's gonna make you jump ship, honestly. Moo makes new kinds of errors possible. Traces that lie about what a program did. Huh? Okay, so that's bad. Opcodes that are easy to mistype, of course. But if we truly believe that the software development process should prioritize comprehension over ease of authorship, it's worth exploring what we gain by taking on these drawbacks. Yeah, readability over authorability, right? Readability over writability. I think it's a super interesting topic. Um, and you know, although readability is important, writability, like if people can write your bloody programs, can write stuff easily, then people aren't going to read it because how can you read what doesn't exist? So that's like we can't prioritize readability too much. While Moo's built in one-time environment is fairly independent of mainstream software, it still relies on host machine. Okay. Higher-level languages may require greater complexity to implement. If we can't keep them comprehensible, we'll keep them out, which really limits the power of language, doesn't it? Or like the scope it can fit. High-level features provide flexibility and are particularly useful for prototyping. Yeah, I said this before, prototyping. Like some people say that Rust is like hard to, ironically, it's hard to prototype in because of the safety it imposes. Whereas a language like C or C++, like you can very easily just prototype something without worrying about the long-term consequences. Sorry, you can. I can't speak, man. You can very easily prototype something without thinking about the long-term consequences in a language like C or C++, which are kind of lower level anyway. But I guess the same can be said for like Python and JavaScript. Like you can very like they are so high level that you can easily prototype, but those come at the issues of like they may not scale well, in complexity, and of course performance losses. But okay, hmm. If we each had one computer to truly call our own, truly running for our benefit, would it really run at full throttle day in and day out? Our experience with Moo suggests that it might be better to treat performance and much else that we tend to obsess over as something to satisfice rather than optimize. Satisfice. What is that word? Decide on and pursue a course of action that will satisfy the minimum requirements. So suffice and satisfy. I mean, this is the mindset that's already kind of adopted though. Like again, like Java, Python, JavaScript, Go, like they all use garbage collection, and that's already a satisfice, or rather a sacrifice because they sacrifice performance, which is fine for most cases, but like it will also mean that languages like C++ will inevitably just be better for some use cases. Which again, like, should we have this big monolithic everything language, or should we have a language that can fit different domains? And with Zig, I will say, and Odin as well, because you have custom allocators and they're very easy to control, you can create a garbage collector model, like an allocation system that mimics a garbage collector. You can do that, and that already makes like Zig and Odin much more applicable to other languages, right? Like I mean, like the use case of other languages, like Go and this and that. And then really the main thing then is like how much other things can you abstract away? Hey, anyway, creating an entire new stack may seem like cutting out windmills. I don't know, I'm not familiar with that expression. But the mainstream software industrial complex suffers from obvious defects, even in the eyes of those who don't share our philosophy. Projects tend to accumulate inertia and slow down over time. Yep. Security is a constant concern. Yep. And review is lacking in spite of source code being increasingly open and available. AI. Vulnerabilities, when found, often have a high blast radius. Yeah, these problems seem foundational and they are reasons for anyone to explore starting anew. Okay, this paper is something. Let me just. I want to look into this white box thing. A second bit of conventional wisdom around testing is to test only what can be robustly tested. As a consequence, mainstream software doesn't write automated tests, or doesn't write automated tests for performance. Moose traces help here. So far, we've only discussed traces of machine code, instructions running the emulator, but all Mu programs emit a trace. Okay, a versatile append-only and memory log are structured facts deduced about the domain during the course of a program. Huh. Okay, automated tests can now inspect the trace and check not just the final result, but also that it was deduced in the correct manner. This sounds very similar to like proofwriting in languages like Agda and Lean, right? Am I tripping? We can now write stable and robust tests denominated in the units of our choices. Choice, God. For example, a sort function may emit an event to the trace on every swap, thereby permitting a performance test to check that doubling the size of the input doesn't cause the number of swaps to quadruple. Uh, okay. For say testing that a triangle is visible in a graphics pipeline, will that failover occur correctly when the tester crashed in the distributed system? Okay. I don't fully understand what this is, but it does sound interesting. So, yeah, we actually finished that. It's now been what 2.5 hours almost. Um, there was something stood out to me. I think it was here in the summary. Even if Moo's specific orientation doesn't be wrong, because the force is like such a value was investing in the section seem compelling for those who it. Um, I could have sworn I saw something that made me. Nah, I. What was it? Tam. Wait a minute. Okay, actually, most software today is on a trajectory of ever increasing complexity. Features are rarely deleted because they kind of can't be. Over time, complexity invariably reaches a threshold where new features take longer and longer to add. C++. At this point, the project becomes much more selective about adding new features. The result of this trajectory is that early users have a huge impact on the feature set of a program. Ah, that's right. Okay. Often long. I mean, I just remembered my point. Often long after they stop using it. Compatibility, while useful in moderation, has over time the effect of ossifying all the degrees of freedom. Yeah, man, it sucks. It sucks. The freedom constraints of C++ suck. Much of this trajectory stems from people's reluctance to modify software. I would say reluctance. It's also inability. Like if you update C++ and they need to like they have this huge code base that they want to. I don't get it actually. I really do not get the issue with C++, right? If C++2 came out, all it would mean is that like existing code bases don't get the new features. And then if they want to, and then if they want to keep using C++, they're kind of going to fall behind. And then if it's such a big deal, then they need to rewrite they need to rewrite their code base, which they may not always have the resources to do. But like my counterpoint is look at Rust. How many different how many of these huge code bases that people say, like they used to say, if we made C++2, these code bases would suffer. How many of those have now been rewritten in Rust? Like that's not a small thing to to consider, right? Because we've had this fear of like C++ will always exist because these old code bases will always need them, and yet here we have Rust coming in, Zig coming in, and these companies like are actually rewriting their stuff in Rust. Or I mean, some are also rewriting in Zig, but obviously Zig isn't as stable, so that gets less support. But Rust for sure, like it's honestly quite worth talking about. Or Go as well, like even rewriting in Go, like companies are willing to sacrifice that C++ speed. Um, not like Go is slow, but like Go is more practical. In many ways, and the only way that you could combat this, say, oh, but we need performance. Go compromise some performance. Like fair enough, then make your language be like Go, as convenient as Go, with better performance. But instead we're stuck with C++ being the way it is, or C being the way it is. Or like JavaScript being the way it is. Like fucking like, bloody hell. Um, hmm. So okay, with forking, yeah, like if someone, but then the issue, like people obviously have forked C++ and C and all that, and like you have languages like Carbon. I mean, Carbon's been in development for ages, but like you have these quote unquote forks, but they just don't garner my voice cracked. They just don't garner enough attention because maintaining a programming language is not easy. And so really my takeaway, um, okay, my takeaway is uh, can I do this? Hell yeah. My takeaway is like we need to just make more programming languages. Like I have criticized Mu a lot, but that's because it needs criticism. Like we should make more languages like this that test things like this to really see what works, what doesn't, and what can we learn from them. Like I'm not a fan of how Rust. I mean, there's a few examples, but for one example is Rust, right? Rust markets itself as the everything language, and that it will be the final frontier. Um, and surely, like it definitely has a lot of features that will make it stand the test of time. Like Rust does enough different, fundamentally different from C++ that it is like that is why it is such a proper competitor and a viable replacement. Like, because I mean, even just tagged unions aside and all that, even just the the ownership model of the borrow checker is so fundamental. People are asking for like other ways for ways that for C++ to implement it because it's just so useful. But even then, even as good as Rust seems right now, Rust will inevitably face issues in the future that hold it back. And the only way that it could possibly circumvent those is to have like major language redesigns. Um, so I like that Rust has an addition feature, but I'm also worried that even then the Rust team will be hesitant to make changes that are too big because they don't want to alienate people. Which kind of which kind of highlights a bigger issue just in general, which is that. Sorry, I just realized that like my face is covering this, so this probably looks trippy as hell. Let me go somewhere else. Um, but like it kind of shows that have an issue as programmers in that if our language were to change in a major way, for the better, by the way, but like if it were to change in a major way, we'd be so hesitant to jump ship. Uh, not sorry, not jump ship. We would be hesitant to update because we just want to stay with what we're familiar with, as opposed to evolving with the language, right? Um, so it's not even like really an unsolvable issue. Like people treat the C++ backwards compatibility issue as if it's like this thing that just will always exist. But if programmers are just a bit more open to again to evolving with the language, then I mean, to be fair, it's not just programmers, the companies as well, the people they work for need to be willing to also update it. Um, then we would be in a better situation. That being said, if you have old code bases, then of course you need to like change things. But then like languages can do things as they update to make it easier for programmers to port their code bases, right? Like Rust has interoperability with its older editions because each module is contained in an edition. But as long as the interface is the same, then it's not so much of an issue. But like, what if down the line Rust came to a problem where it needed to like abandon its ownership module and have some other system for ownership? Like, is that the kind of change that Rust would be willing to make? Right? Like, could C++ in the foreseeable future ever change its model to have some kind of ownership model or change its defaults? Like things that would require existing code bases to change um, if they want to update it to the latest version, right? But even then, like I find it so funny that like funny in like a weird funny kind of way that people that C++ goes through all this effort to maintain backwards compatibility, and yet we still have programmers who just refuse to like go past C++ 17 or even like C++11, um, because they want to like prohibit or like I guess like limit the number of new features they have. Like, why can't a an old code base be on C++ 26? Like, if they're not going to do that anyway, then who are we maintaining backwards compatibility for? Like, I think C++ could honestly make a case for just cutting off at this point. Um, but, maybe maybe there are actually people and cases out there where they do use the latest C++, but they also have legacy code that they need to maintain. And part of that issue is because of C's horrendous module system. Um, I mean, actually, mind you, I think modules will be the start of C++ really beginning to shift for the better. Because like with includes, you like the problem of legacy code is a real issue because you can't just hide well, not hide. You can't wrap the legacy code in its own version. You need to copy paste it into newer versions of C++ as well. But with modules, the new module C++ system, right, coming in, well, that's come in C++ 20 and is very slowly being implemented into like GCC and Clang and all that. Once that comes, I really hope it offers a way to mix old legacy code with new code in such a way that we could actually see features be deleted. That would be huge. Um, but yeah, that's my issue with Rust, in that I fear it may not make those big changes despite having an addition system, and that another language one day will come along anyway and replace Rust, which is like not a huge issue necessarily, but like it definitely creates issues for those code bases right now that are relying on Rust being a forever language. Um, or with Zig, my big issue with Zig is that it doesn't seem to want to care about legacy support either, like at all. Like it just wants to keep on rebuilding itself, changing itself until it feels that it is perfect enough to be published, to be released in version 1.0, and then only make minor updates from then on. Like no major feature additions. Anything that's major would be a Zig 2.0, which is interesting. But I think what we should be doing, and I know the industry needs languages that are stable, whatever, but I think even with Rust and Zig, we should really be putting like we should be putting experimenting more with custom languages, with trying out different languages. Like create Rust, but then don't advertise it as a forever language. Advertise it as um a language that may evolve, or a language that may be replaced by a better language, and then Rust is abandoned, and we get a new language. And again, it's problematic for legacy code base issues. It's problematic for adoption issues. People don't want to adopt a new language all the time. It's problematic because we need programs that work now and will continue working. You know, but that can be maintained. And it's also an issue because like if Rust doesn't advertise itself as a forever language, then how the hell is it going to replace C++? Because people rely on C++ being a forever language as well, quote unquote. So yeah, it's not a simple solution, but I do like seeing new languages like this, like Moo and I don't know, like whatever other people are making. And I really look forward to seeing what developments it makes. And I just kind of I wish that we as programmers were more open to different ways of programming, different ideas, right? Um, yeah. Anyway, there's a lot more I could say in like a blog post or something, but in fact, you know what? I'm gonna write this too. Like, why do people fear functional programming? Because like there are genuine like drawbacks to functional programming, um, as opposed to procedural programming. Like genuine reasons why it can be worse, but like that's not what stops people from learning functional programming. What stops people from learning like Haskell or OCaml is that they literally just cannot wrap their heads around the concepts. I mean, and by cannot, I mean they can, but they just don't make the effort to, or like they don't try. They give up before they succeed, and I think that's really unfortunate. My voice is cracking now. Um, we should be more open to learning. That is my conclusion. Anyway, thanks for watching. Subscribe for more videos about stuff.